Good morning, students. Estimation part 4 in this video includes methods of moments, methods of least squares, and also Cramer-Rao lower bound. Rao-Cramer lower bound. Three topics are very, very important. Methods of moments and the methods of least squares is the method of estimations. Cramer-Rao lower bound gives variance lower bound. So these three topics are very, very important for the examination point of view. Starting with methods of moment, MME is very simple topic, easiest topic, methods of moments, MME. Estimation by the method of moments was introduced by Carl Pearson. Carl Pearson method. Here we have to equate the population moments and sample moments and solve it. We get method of moments. That is simple concept. Equating the population moments and sample moments, solve it, we get estimators, method of moment estimators. Now this is a procedure. Let f of x comma theta 1 theta 2 theta k here, theta k, be the density function of a distribution, probability density function of a distribution. Now mu r dash formula, integral minus infinity plus infinity x power r into PDF of x dx. Here r is equal to 1 to k. So that mu1 dash r value 1 to k, mu1 dash, mu2 dash, muk dash are the functions of theta 1, theta 2, theta k. Let xi, I is equal to 1 to n be a random sample of size n from a given population. The method of moments consists in solving k equations theta 1, theta 2, theta k in terms of mu1 dash, mu2 dash, muk dash, and then replacing these moments mr dash, mu r dash, r is equal to 1 to k by the sample moments mi dash equal to summation xi by n. So here is summation xi power, here is summation xi power I by n. Here is I is equal to 1 m1 dash summation x power 1, I is equal to summation x power 2 by n, I is equal to 3 summation x power 3 by n, I is equal to 1 to k, I is equal to 1 to k, I is equal to 1 to k. That is theta 1 cap is equal to m1 dash first sample moments, theta 2 cap is equal to second sample moment, theta cap is equal to so kth sample moment. Then by the method of moments, theta 1 cap, theta 2 cap, theta k cap are the required estimators of theta 1, theta 2, theta k respectively. This is the original procedure. I am giving the simple concept here, easiest way for the examination point of view. Here, population, this is a population. Population parameter is theta. Here is population moment denoted mu r dash. So now here calculate the population moment, rth population non-central moment. The formula is summation x power r into p of x. X is discrete random variable case. X is DRV. X is DRV. For continuous random variable, minus infinity to plus infinity, x power r into f of x dx. X is continuous random variable. Now here is draw the sample from this one. The sample statistic is called T. The sample moment mr dash that is equal to summation x power r by n. So unique formula here to calculate the population population's non-central moment. So in two ways here, either discrete random variable or continuous random variable. Here a sample is drawn from this one. The sample size is n. Sample is drawn from this population with size n. Statistic is T is called statistic function of sample observations. Now here calculate the rth sample moment. This is called rth sample non-central moment about origin non-central moment. Here BR dash is called rth population non-central moment. Non-central moment. Now equating these two, BR dash equal to MR dash and solve it. We get MMEs, method of moment estimators. MMEs. This is the procedure. Easily we can. So obtain the MMEs. Several properties are there. First property, for estimating the population moments, the MMEs are consistent and unbiased estimators. Consistent and unbiased estimators. MMEs are consistent and unbiased estimators. Easily we can identify the consistent estimator and the unbiased estimator using the MMS technique. MMS are very simple technique. Using that one, easily we can give the consistent and unbiased estimators. No need to take the original process of consistency and unbiased. So directly how to take these MMEs, easily we can give the consistent and unbiased estimators. estimators will be less efficient estimator than the MLEs. So through MMEs, the variance of any statistics through MMEs is here is greater than, so variance of MLE estimator is variance of MME estimator is greater than variance of MLE estimator. So we can say that MM estimators less efficient estimator than MLEs. So MMEs are asymptotically normal distribution. It's very important. Asymptotically, by taking limit concept, MMEs are definitely follows normal distribution. MLEs also asymptotically normal distribution. So properties also explained. Concept and properties given. Next, third one, another very popular method of least squares. I already explained this concept in the curve fitting video lessons. Refer the curve fitting video lesson. Already sir explained method of least square techniques. Same procedure, same techniques applied here, and also you have to find out the method of least square estimators. In curve fitting chapter, we have discussed in detail the method of least square for fitting a straight line, parabola, exponential, and power curves. So now here is using that principle of least square techniques. Easily we can fit a straight line, parabola, exponential, and power curves. Those estimators are called method of least square estimators. So you have to use the same procedure, see same techniques, properties, and apply the same procedure and concept, and find out the method of least square estimators. That the method of least square estimators obtained as a linear function of the y's will be minimum variance unbiased estimators. Remember this point is very important bit for the examination. Method of least square estimators obtained as a linear function of the y's will be minimum variance unbiased estimators. Minimum variance unbiased estimators. Next, several examples. Problems on MMEs. Problems on method of moments. First problem, X follows binomial n comma p. That xi follows. Random sample is drawn from this Bernoulli population. I is equal to 1 to n. MME for P dash. Solution. Xi follows binomial n comma p. Here is E of x is equal to np. E of x is equal to np, same as to first population moments. What is the procedure here? First of all, you have to calculate the first non-central moment of this random variable. If you know the properties of this given distribution, directly you have to write the first population moment, and immediately you have to take the first sample moment, that is m1 dash equal to summation x by n. Here is r is equal to 1. So now this is equation 1, this is equation 2. Equating 1 and 2, we get m1 dash equal to mu1 dash, implies summation xi by n is equal to np. mu1 dash equal to np. Our requirement is p here. P is equal to summation xi is called x bar by n. This is p cap. Therefore, MME of P is equal to x bar by n. MME of P is equal to x bar by n. This is very simple one. This is unbiased estimator of parameter P. It is also a consistent estimator of parameter P. Easily we can give the consistent and unbiased estimators using MMEs. But MMEs are less efficient estimator than the MLEs. Second problem, Xi follows Poisson lambda, single parameter. I is equal to 1 to n. I is equal to 1 to n. MME of lambda is dash. That here Xi follows Poisson lambda. mu1 dash. Using the properties of Poisson, the mean of Poisson is lambda. So now immediately you have to take the, one parameter is required here. One parameter is to be estimated. In this case, one population moment and one sample moment is required. Suppose two parameters to be estimated, two population moments, two sample moments are required. In this case, this random variable this distribution has only one parameter. To estimate that parameter, one population moment, one sample moment is required. So M1 dash is formula. So 1 by n summation xi. It is called x bar. Now mu1 dash equal to m1 dash implies lambda is equal to x bar. Therefore, MME of MME for lambda or of lambda x bar. So MMEs are consistent unbiased estimators. MMEs are consistent and unbiased estimators. Example 3. X follows exponential parameter 1 by theta. So I is equal to 1, 2, 3 and so on n. MME of theta dash. Solution. E of xi is equal to v1 dash equal to theta. Here is parameter 1 by theta. Mean is equal to theta. Now m1 dash equal to summation xi by n. It is denoted as x bar. Equating v1 dash and m1 dash implies theta is equal to x bar. Therefore, theta cap is equal to x bar. MME of theta is equal to x bar. Xi follows uniform a comma b. I is equal to 1, 2, 3 and so on n. MME for a and b dash. Here there are two parameters. First of all, here PDF 1 by b minus a less than or equal to x less than or equal to b. There are two parameters. In this case, two population moments and two sample moments are required to estimate A and B. So now mu1 dash of this population based on property B plus A by 2. Next mu2 dash is equal to B square plus AB plus A square by 3. So now m1 dash equal to x bar summation xi by n. M2 dash equal to summation xi square by n. There are two population moments and two sample moments. Here you are equating mu1 dash equal to m1 dash and v2 dash equal to m2 dash. v1 dash equal to b plus a by 2. But m1 dash in terms of m1 dash, no need to take here x bar. Directly have to take m1 dash. Our convenience we have to take this m1 dash. Implies b plus a is equal to 2m1 dash. Now, using the v2 dash equal to m2 dash, v2 dash b square plus ab plus a square by 3 is equal to m2 dash. Implies b square plus ab plus a square is equal to 3 into m2 dash. Now, b plus a whole square minus ab is equal to 3 m2 dash. Implies b plus a is equal to From this one, this is equation 1. B plus A is equal to what? 2m1 dash. 2m1 dash. B plus A 2m1 dash whole square is equal to 3m2 dash plus AB. So now AB is equal to 4m1 dash whole square minus 3m2 dash. Now B plus A whole square. So B minus A whole square formula. To get A and B, use the algebra formula, that is B minus A whole square is equal to B plus A whole square minus 4AB. B plus A is what? 2m1 dash whole square minus 4. AB is what? 4m1 dash square minus 3m2 dash. That is equal to 4m1 dash square minus 4 4s are 16 m1 dash square plus 12 m2 dash. Now 12 m2 dash minus 12 m1 dash whole square, that is B minus A whole square. So B minus A is equal to the positive square root of 12 m2 dash minus 12 m1 dash whole square. Now B plus A is equal to 2 m1 dash. Now solve this 2. Here is we get minus A plus A cancel. 2B is equal to 2m1 dash plus square root of 12 m2 dash minus 12 m1 dash whole square. B cap is equal to m1 dash. 12 is common. 4 3s are 12. 2 is taken outside. So the remaining part here, square root of 3 into m2 dash minus m1 dash whole square. That is the B cap value. Now substitute B cap in any one of the above equation. We get A cap. A cap is equal to m1 dash minus, by substituting B cap in any one of the equation, we get A cap is equal to m1 dash minus 3 into m2 dash minus m1 dash whole square. Therefore, MME of A is equal to m1 dash plus square root of 3 into m2 dash minus m1 dash whole square. MME of B is equal to m1 dash minus square root of 3 into m2 dash minus m1 dash whole square. Oh, a two parameters case. Continuous uniform distribution, MMEs are obtained. Example 5. Let xi follows normal distribution mu comma sigma square I is equal to 1 to 1 so on n. MME for mu and sigma square. So now here xi follows normal mu comma sigma square. The two parameters, two population moments and two sample moments are required. E of xi mu1 dash equal to mu. Next mu2 dash equal to sigma square plus mu square. The formula is already given. Variance of x plus e of x whole square. mu2 dash formula. So now m1 dash equal to summation xi by n. m2 dash equal to summation xi square by n. Now equating mu1 dash equal to m1 dash implies mu is equal to summation xi by n. This is called x bar. This is mu cap. Therefore, MME of mu is equal to sample mean x bar. Now, to calculate the MME of sigma square, m2 dash equal to mu2 dash equal to m2 dash implies mu2 dash sigma square plus mu square is equal to summation xi square by n. Sigma square is equal to summation xi square by n minus mu square. MME of sigma square is equal to summation xi square by n minus mu square. Here mu is known case. Mu is known case. Suppose v is MME of sigma square. Mu is unknown case. In this case here, replace mu by x bar because x bar is a MME of MM estimator of mu. Now here is x bar square. This is same as to small x square. This is mu is unknown case. So now the MME of sigma square is sample variance. So when mu is unknown case. So method of moments estimators, definition, concept, procedure, and important properties, and also live examples are explained. So second, here is method of estimation is over. Third one is least square method, but least square method already explained in the curve fitting chapter. Refer the curve fitting video lessons. Next, another very important, Cramer-Rao inequality. Cramer-Rao inequality. Cramer-Rao inequality provides the variance lower bound. Cramer-Rao inequality provides lower bound to the variance of unbiased estimator of g of theta. That is the complete sentence. Statement: if t is an unbiased estimator of g of theta, a function of parameter theta, g of theta is a function of parameter theta, then the variance lower bound. Actually, variance is greater than 0. Least variance gives consistent values. That least variance is the more efficient estimator. So now here is variance of t. T is unbiased estimator. Variance of t is greater than equal to d by d theta of g of theta, d by d theta of g of theta whole square by expectation of dou log L by dou theta whole square. That is equal to d by d theta of g of theta is called g dash of theta. G dash of theta whole square. So the denominator value is denoted as I of theta. I of theta is the Fisher's information about theta supplied by the sample. Fisher's information about theta supplied by the sample. So I of theta is very, very important. It's a direct question for the examination point of view. Yes, what is I of theta? Fisher's information about parameter theta supplied by the sample. So Kramer-Rao inequality provides a lower bound to the variance of an unbiased estimator of g of theta. That is the importance. So we have some regularity conditions. These regularity conditions satisfied, you can apply the Kramer-Rao inequality. First regularity condition, parametric space H circle is a non-degenerate open interval in the real line. Degenerate means solution is 0. Non-degenerate means not equal to zeros. Non-degenerate open interval on the real line are of minus infinity to plus infinity. First regularity condition. Parametric space must be a non-degenerate open interval on the real line. For almost all x, x1, x2, xn, and for all theta belongs to parametric space, the first derivative exists here. Dou by dou, dou log L by dou theta exists. The exceptional set, if any, is independent of theta. Third one, the range of integration is independent of parameter theta. That is important. The range of integration is independent of theta. So that f of x comma theta is a differentiable under integral sign. The PDF is differentiable under integral sign. The conditions of uniform convergence of integral are satisfied so that differentiation under the integral sign is valid. Integral sign invalid. The conditions of uniform convergence of integrals are satisfied so that differentiation under the integral sign is invalid. One more regularity conditions, but degree level, so no need to check these regularity conditions. We have a few problems in the included in the syllabus. So direct problems, there is a process to MVBs, minimum variance bound estimators, using Kramer-Rao inequality. Here I of theta defined as expectation of dou by dou theta log L of x comma theta whole square. This is the I of theta formula. Exists and is positive for all theta belongs to parametric space. These 5 are the regularity conditions. In advanced level, you have to check the regularity conditions. After that, you have to apply the Kramer-Rao inequality. In degree level, directly you have to go to the using the remarks easily we can. So find out the MVBs, minimum variance bound estimators. So now first remark, if T is unbiased estimator of parameter theta, expectation of T is equal to theta is unbiased estimator, that is G of theta. G of theta is equal to theta. G dash of theta is equal to 1. Then from Kramer-Rao inequality, we get variance of T. T is unbiased estimator greater than or equal to G dash of theta whole square. 1 square means 1 by I of theta. Expectation of dou log L by dou theta whole square. Expectation of dou log L by dou theta whole square. This is called I of theta. So simple variance of T greater than or equal to 1 by I of theta, where I of theta is called the RA Fisher's as amount of information on theta supplied by the sample x1, x2, xn. And its reciprocal 1 by I of theta as the information limit to the variance of estimator T. So now here is reciprocal of 1 by reciprocal of I of theta is the variance of estimator T. So this is very important remark. Second one, an unbiased estimator T of G of theta for which Kramer-Rao lower bound is attained is called Kramer-Rao lower bound is attained. So minimum variance bound estimator is exist. Minimum variance bound estimator is available. The T is called minimum variance bound estimator. Raman-Rao lower bound is attained, so we get minimum variance bound estimators. That is called MVB. The quantity I of theta is called Fisher's information about parameter theta contained in the observation capital X. So I of theta defined as like this. Basic level expectation of dou log L by dou theta whole square. So in terms of second order derivatives, here is minus expectation of dou square log L by dou log L. By applying this simplification, we get this one. Second order derivatives are considered here. In terms of PDFs, dou by dou theta log f of x comma theta whole square. So multiply with n. So here is this may be written as like this. Both are same. Minus n into dou square log f by dou theta square. F is called a PDF of x. Using this I of theta formula, so we can calculate the Fisher's information about theta. So fourth one, the necessary and sufficient condition for unbiased estimator T to attain the lower bound of its variance is given by. So this is the condition. So this is a necessary and sufficient condition for unbiased estimator T to attain the lower bound of its variance. So this is a statement. Dou log L by dou theta, T minus G of theta by lambda of theta, T minus G of theta into A of theta. A of theta is equal to 1 by lambda of theta. If is very shortcut formula to get MVBs, the likelihood function you know very well here. In the previous videos, I explained the concept of the likelihood functions. So the likelihood function L can be expressed as in the form of dou log L by dou theta, T minus G of theta by lambda of theta, T minus G of theta into A of theta. Then, so that likelihood function can be expressed like this. In this case, T is a function of sample observation, is a statistic. T is unbiased estimator of G of theta. The minimum variance bound estimator for T, estimator T for G of theta exists in this case. Finally, variance of T. We have to calculate the variance of T using the formula G dash of theta. This is the G of theta, differentiation of G of theta into denominator value lambda of theta. Take modulus, apply modulus. That is variance because variance is always greater than 0. So now here is that likelihood function can be expressed in the form of dou log L by dou theta is equal to T minus G of theta by lambda of theta. Easily we can get MVBs and minimum variance So finally, we have important property. Minimum variance bound estimator for G of theta exists if and only if there exists a sufficient estimator of G of theta. MVB exists if and only if there exists a sufficient estimator for G of theta. So to identify the sufficient estimator of the given problem, so is very typical one. In this case, we have to take this MVB estimators. That MVB estimator exists of parameter theta if and only if there exists a sufficient estimator for G of theta. The given function for the given PDF or probability mass function, if sufficient estimator is exists or not, to identify that one, first of all you have to find out the minimum variance bound estimator. Minimum variance bound estimator exists automatically. There is a sufficient estimator for G of theta. That is the rule. So that is the importance of the Cramer-Rao inequality. So we are going to discuss about some few examples. Problem 1. Let xi follows Poisson lambda IIDs, IID random variables. I is equal to 1 to n MVB for lambda dash. Very, very important one. So now here, first of all, likelihood function. I is equal to 1 to n P of xi comma lambda. I is equal to 1 to n e power minus lambda, lambda power xi by xi factorial. L is equal to e power minus n lambda, lambda power summation xi by pi xi factorial. Now take log both sides. Log L is equal to minus n lambda plus summation xi I is equal to 1 to n log lambda minus log of pi xi factorial, purely constant term. Dou log L by dou log L by dou lambda is a common procedure for MLEs and MEBs is equal to MLEs. So this differentiation equal to 0, but in this case, don't this differentiation of logarithm not equating to 0. So now here find out the differentiation of log L with respect to lambda. So minus n plus summation xi I is equal to 1 to n bracket here is 1 by lambda. Now this can be expressed as 1 can be expressed as dou log L by dou theta is equal to t minus g of theta by lambda of theta. Now dou log L by dou lambda is equal to, so now here is t is a function of sample observations, summation xi by lambda minus n. Dou log L by dou lambda is equal to, by taking LCM, summation xi minus lambda n by lambda. Now, so this is not equivalent to t minus g of theta. Now convert into this numerator value in terms of t minus g of theta. That is equal to numerator denominator dividing by n. Summation xi by n is purely function of sample observations. So this is purely function of g of theta here by lambda by n. This is this one. Now dou log L by dou lambda. Dou log L by dou lambda is equal to x bar minus lambda by n is equivalent to p minus g of theta by lambda of theta. Therefore, here is the x bar is unbiased estimator of lambda. This is the first one. Second one, MVB for lambda is x bar. Third one, variance of x bar is equal to modulus of c dash of theta into lambda of theta. In our problem, g of theta is equal to, in place of g of theta, we have a lambda, or g of theta or g of lambda. So implies here g dash of theta is equal to lambda. I'm sorry. With respect to lambda here, that is called 1. Lambda of theta is equal to lambda by n. Therefore, variance of x bar is equal to modulus 1 into lambda by n. That is equal to lambda by n. So minimum variance bound estimator obtained. Second example. Let xi follows n of u comma sigma square. I is equal to 1 to 1 so on n. MVB for mu sigma square is known case. Sigma square is known case. Solution. The likelihood function I is equal to 1 to n 1 by sigma. Directly substitute the PDF 2 pi e power minus half x minus mu by sigma whole square. L is equal to 1 by sigma root 2 pi whole power n e power minus half summation I is equal to 1 to n xi minus mu by sigma whole square. Log L is equal to here minus n log sigma root 2 pi. Log 1 is equal to 0. Log a by b is equal to log a minus log b. Log 1 0. So directly this value minus n into log sigma root 2 pi, purely constant value, minus half 1 by sigma square summation I is equal to 1 to n xi minus mu whole square. Now differentiate 1 with respect to mu. We get dou log L by dou mu is equal to purely constant 0 minus 1 by 2 sigma square constant is x square format 2 into summation I is equal to 1 to n xi minus mu multiply with minus 1. Dou log L by dou mu is equal to 2 cancel minus minus plus 1 by sigma square summation xi minus mu. Here I is equal to 1 to n. Now this is equal to 1 by sigma square. So this is equal to summation xi is nx bar summation mu is equal to n mu. Now this is n into x bar minus mu by sigma square. So numerator, denominator dividing by n. X bar minus mu by sigma square by n is same as to p minus g of theta by lambda of theta. Now therefore 1 x bar is unbiased estimator for mu. Second one MVB for mu is equal to x bar. Third one variance of x bar is equal to g dash of theta. G of theta is equal to mu. G dash of theta is equal to 1. Lambda of theta is equal to sigma square by n. Directly by substituting here, the formula is g dash of theta into lambda of theta. That is equal to g dash of theta is equal to 1. Lambda of theta sigma square by n. Sigma square by n modulus. That is equal to sigma square positive n positive. No need to take modulus. The variance of x bar sigma square by n. This is the lower bound for the statistic x bar. Example 2 is very, very important. Third example. Let xi follows Cauchy population. Parameter 1 comma theta. I is equal to 1 to n. MVB for theta relation. The likelihood function is equal to I is equal to 1 to n 1 by pi 1 plus xi minus theta xi minus theta whole square. This is the PDF of Cauchy distribution. I is equal to 1 to n apply the pi here. This is 1 by pi is a constant. Pi means product value 1 by pi whole power n. I is equal to 1 to n 1 by 1 plus xi minus theta whole square. Take log both sides. Log L is equal to minus n log pi, purely constant. Here plus log A into B is equal to log A into B is equal to log A into B is equal to log A plus log B. Log of I is equal to 1 to n 1 by 1 plus xi minus theta whole square. So now here log L is equal to minus n log pi. Here is log A by B formula. Apply this one minus summation I is equal to 1 to n log of 1 plus xi minus theta whole square. So this is the equation 1. Differentiate 1 respect theta. We get dou log L by dou theta is equal to 0. Here is minus, here is minus here, plus 2 into summation I is equal to 1 to n. The differentiation is xi minus theta by log, differentiation of log function is 1 by x, 1 plus xi minus theta whole square. So dou log L by dou theta is equal to 2 into summation I is equal to 1 to n xi minus theta by 1 plus xi minus theta whole square. This cannot be expressed as t minus g of theta by lambda of theta. Never. This is cannot be expressed as t minus g of theta by lambda of theta. Therefore, MVB does not exist for parameter theta. For Cauchy population, MVB does not exist. MVB does not exist. One more example. Let xi follows xo of parameter 1 by theta. I is equal to 1 to and so on n. MVB for theta dash. The likelihood function phi I is equal to 1 to n theta into e power 1 by theta into e power minus xi by theta, that is equal to 1 by theta power n e power minus summation xi by theta. Now, by applying logarithm, by taking logarithm both sides, minus n log theta minus summation xi by theta. This is 1. Differentiate 1 with respect theta, we get dou log L by dou theta is equal to minus n by theta plus summation xi by 1 by theta differentiation, 1 by x differentiation. So minus plus here by theta square. So dou log L by dou theta is equal to summation xi by theta square minus n by theta. Theta square LCM summation xi minus n theta. Numerator denominator dividing by n. Summation xi by n minus theta all divided by theta square by n. That is equal to x bar minus theta by theta square by n is same as to t minus g of theta by lambda of theta. So therefore, 1 x bar is unbiased estimator of unbiased estimator of theta. Second one, MBB for exponential distribution parameter theta is x bar. Third one, variance of x bar is equal to modulus of g dash of theta into lambda of theta. So now g dash of theta 1, lambda theta, theta square by n. Here, g of theta is equal to theta. G dash of theta is equal to 1. Therefore, variance of x bar is equal to theta square by n. Oh, this is very important examples. Raman-Rao inequality statement, regularity conditions, important remarks, solid examples are explained. So, theory of estimation part 4 is over.